Electrolysis. So electrolysis is when we use electrical current to drive a reaction that would not be spontaneous. So we can make a non-spontaneous reaction happen. So the reaction between hydrogen gas and oxygen gas to create water is spontaneous, and so that can be used to produce electrical current. But by supplying electrical current, we can cause the reverse reaction to occur. So we could have a solar-powered electrolytic cell generating generating hydrogen to power fuel cells. So if we run this reaction backwards, we can create hydrogen, and then you put the hydrogen in the fuel cell and run your car or whatever. This illustrates that idea. So we've got water. There's no point in doing that. Other uses of electrolysis. Most metals occur naturally as oxides. And so you don't just find sodium metal sitting around. And so if you want the metal, then one way that you can get it is by electrolysis. So sodium metal is produced by the electrolysis of melted sodium chloride. Another thing you can use electrolysis for is plating metals onto other metals. So a solid silver set of silverware, hence the name silverware, would be very, very expensive, right? But if you take a less expensive metal and just put a layer of silver on the outside, this is called silver plating. Silver-plated silverware is a lot less expensive because it isn't solid silver. So that reaction is not spontaneous, but by using electricity we can drive it. And so this illustrates that happening. Here's the object that we're plating, and we've got a silver electrode over here, and so the silver ions are going to be formed here at the anode, and then they're going to be reduced again at the cathode. And so they will coat or plate onto that object. The voltage needed to do electrolysis depends on the specific half reactions that are involved. And here we have a zinc-copper voltaic cell where we've got the zinc electrode over here as the anode and the copper as the cathode. If we use electrolysis, we can drive the reaction in the other direction. And so now we're reducing zinc ions and oxidizing copper ions. So these half reactions are backwards. Now the zinc becomes the cathode because reduction always occurs at the cathode and oxidation always occurs at the anode. So this slide gives us a summary. All electrochemical cells, we've got oxidation at the anode, reduction at the cathode. In voltaic cells, the anode is the source of electrons, so it's negative, and the cathode draws the electrons away, it's positive. In electrolytic cells, electrons are drawn away from the anode, so the anode is positive, and electrons are forced into the cathode, connected to the negative terminal of the power source, and so the cathode is negative. Okay, so which statement is true for both electrolytic and voltaic cells? The cell spontaneously produces a positive voltage. Electrons flow from the anode to the cathode, or oxidation occurs at the cathode. In all electrochemical cells, oxidation occurs at the anode, reduction occurs at the cathode. So this oxidation occurs at the cathode. That's just wrong, right? That's wrong, right? That's right, wrong. Electrons flow from the anode to the cathode. Here, the anode is the source of electrons, and they're flowing to the cathode. Here, electrons are moving away from the anode towards the cathode. So that's our correct answer. The cell spontaneously producing a positive voltage is only true for a voltaic cell. It's not true for an electrolytic cell. So, predicting electrolysis products, it's not as simple as it might seem. If we're doing pure molten salts, then things are easy. The anion gets oxidized, the cation gets reduced, because those are the only things present. There's nothing else there. So if you've got molten sodium chloride, the chloride is already reduced. It can't be reduced anymore, so that's what gets oxidized. The sodium can't be further oxidized, so it's reduced. If you had a molten salt with more than one cation, then things would get a little more complicated. Whichever cation would be more easily reduced is what would happen. The note here is that those standard cell potentials that are given do not apply to molten salts. They apply to aqueous solutions at 1 molar concentrations, but the relative ordering is the same. So even though you can't tell what the voltage is, you can tell which one is more easily reduced. So the example here, if you had sodium chloride and potassium chloride mixed together, what would happen? Well, sodium is reduced at minus 271 volts. Potassium is reduced at minus 292 volts. Sodium is easier to reduce, and so the sodium will get reduced and the potassium will not. If we have more than one anion, again, we have to look at which one is easier. The anion gets oxidized. Which one's easier to oxidize? So if we've got sodium bromide and sodium chloride, here we've got the bromide going to bromine plus 2 electrons. This is an oxidation. Chloride going to chlorine plus 2 electrons, also the oxidation. So the way I think about it is when I reverse the equation, I change the sign. And so then you've got a list ordered with positive at the top. The higher reaction is easier. The textbook always gives reduction potentials, even if the oxidation is shown. Makes me crazy. But bromide is easier to oxidize. In aqueous solution, we've got the added factor of the possibility of water being electrolyzed. So water can undergo an oxidation to form hydrogen ions and oxygen gas. It can undergo a reduction to form hydrogen gas and hydroxide ions. These are the standard potentials, but the standard potential would have hydroxide ion as 1 molar and hydrogen ion as 1 molar, and that's not true in pure water. So in pure water at room temperature, those concentrations are not standard. So these are the concentrations at room temperature in pure water, negative 0.82 volts and negative 0.41 volts. So in a cell, we would have the cell potential of minus 1.23 volts. So you could drive this reaction. Now, pure water doesn't conduct electricity, so that's kind of a problem. But if you add an electrolyte to the solution, then we can have electrolysis occurring. So, an example would be sodium iodide in solution. So, water being oxidized in regular conditions is minus 0.82 volts. The iodide being oxidized is minus 0.54 volts. The reduction of water is minus 0.41 volts. The reduction of sodium is minus 2.71 volts. So at each electrode, the half reaction that is the easiest, that is less negative, will actually occur. And so you're going to see iodine, the iodide being oxidized to iodine, because this is less negative. But you are going to see water being reduced because it's easier to reduce than sodium. So you can't reduce cations of active metals in aqueous solution because the water gets reduced before those active metal ions do. And then, just because it isn't complicated enough, there's the additional complication of the overvoltage. Overvoltage is an additional voltage that has to be applied to get some non-spontaneous reactions to occur. So water being oxidized to oxygen and hydrogen ions has a potential of negative 0.82 volts, but the actual voltage needed is more like 1.4 volts. So that's a little different. These factors are known, but they're beyond the scope of this course, and so we're not going to talk about them. But there is this overvoltage. So in an electrolytic cell, electrons act like a reactant, and they have a stoichiometric relationship with other reactants and products. So this is the electrolytic cell for copper plating. Here they've got a spoon over here and a voltage source, and they're going to deposit copper ions onto this spoon electrode over here. Well, the half reaction is copper ion plus 2 electrons makes solid copper, the element. And so this 2 is a stoichiometric relationship. So 2 moles of electrons for every 1 mole of copper. Well, we don't measure the quantity of electrons with mass, we measure them with charge. And we can determine the number of moles of electrons from the total charge that has flowed through the cell. And the total charge is going to depend on the magnitude of the current and the time. So the Faraday's constant is 96,485 coulombs per mole. So this, if we have the coulombs, then we can figure out how many moles. An amp is a coulomb per second. So the current in coulombs per second, or amps, times the time that it runs in seconds gives us the charge. And this charge in coulombs can be converted to moles of electrons. So silver plating uses the reaction Ag plus electron to Ag. How many moles of electrons must pass through an electrolytic cell for silver plating in order to plate 3 moles of silver? We want to look at this half reaction and say, what's the relationship between moles of electrons and moles of silver? Well, it's 1 mole to 1 mole. So if we want to plate 3 moles of silver, we need how many moles of electrons? Three. Okay, so silver can be plated out of a solution containing silver according to this half reaction. How much time in minutes would it take to plate 12 grams of silver using a current of 3 amps? So 3 amps is equal to 3 coulombs per second. We've got 12 grams of silver. Coulombs per second gives us a relationship between charge and seconds. And then we've got Faraday's constant, coulombs per mole of electrons. So this allows us to relate charge to moles of electrons. And the balanced chemical equation gives us the relationship between moles of silver and moles of electrons. 1 mole of electrons per 1 mole of silver. And then from the periodic table, we know that there are 107.9 grams of silver per mole of silver. So we can take our 12 grams of silver and convert that to moles. Sorry. Shoot. Did I really lose it? So I did that wrong. 107.9 grams per mole of silver. And then I can convert that to moles of electrons. And I can convert that to coulombs. And finally, I can convert that to seconds. And then I need to throw in the relationship between minutes and seconds because the answer asks for minutes. And there is dimensional analysis. Grams of silver canceling, moles of silver canceling, moles of electrons, coulombs, seconds, and we're left with minutes. So 60 minutes.